So last time we saw that the derivative of the exponential function turned out to be itself, that the derivative of e to the x is e to the x. So accordingly, we were able to come up with a very nice antiderivative formula. The antiderivative of e to the x dx is e to the x plus c. And so then we did this example right here, the antiderivative of e to the 2x. And you know, the problem is there's a 2x here, but in our formula, there's just a single variable. There's not 2 times the variable, there's just x there. So no problem, we did a u substitution here. We said, well, let's just let 2x equal u. So then we were able to complete the u substitution. And so using that u substitution, we're able to convert the original integral into 1/2 e to the u du. And then we were able to get to the final answer here. And this, you know, is something we could check by differentiating. And so I wanted to mention that now in general, when we come across an antiderivative that's e to the nx dx, where n is a constant, we're not going to do this u substitution anymore. Because of this u substitution, we know the answer will be e to the nx plus c, over n plus c. So for example, antiderivative of e to the 7x dx would be e to the 7x over 7 plus c. Or antiderivative of e to the pi x would be e to the pi x over pi plus c. Pi is just a number, right? So yeah, that's one useful u substitution that we'll see a lot and, you know, come across quite frequently. The next example is not difficult. It's just a little weird looking, you know, so I wanted to show it to you so that you can start to get used to seeing things like this. Here, it's the antiderivative e to the 1 over x, all divided by x squared dx. You know, the fact of the matter is the only antiderivative formula I know for e is when it's e to the blah, where in the exponent we just have a single variable, not e to the 1 over a variable, not e to a number times a variable, just e to the variable. So let me try and let 1 over x equal u. So I'm going to try and make this entire exponent just into a single term u. So if we let u equal to 1 over x, remember 1 over x is the same as x to the minus 1. And so du would be negative 1 over x squared. The derivative of x to the minus 1 is minus x to the minus 2. And, you know, by quote unquote coincidence, now we're lucky because we exactly do have dx over x squared does occur in the integral. Yes, it's off by a minus sign, but that's not an issue if it's off by a constant. We can always multiply the inside by a minus and multiply the outside by a minus. So that's what I do here. I multiply on the inside by a minus, multiply on the outside by a minus. I moved the x squared so that it's under the dx. Of course, you don't have to do that. I just like to make it look nice. So now this entire term I can replace with du, and e to the 1 over x will just become e to the u. And then I copy down the minus sign in front. And now we have the antiderivative of something where we know the formula for it. So I know the antiderivative of e to the u is e to the u plus c, and then there's a minus sign on the outside, which I copied. Technically, that minus sign distributes to the constant, but minus 1 times a constant is just another constant, which we call c. The very last step here is to go back to the original variable. The problem was given to us in terms of the x variable. So I replace u with 1 over x here for my final step here. And of course, we should be able to always check our answers, you know, by taking the derivative. Here we use a chain rule. So this next example is a little tricky, you know, and I wanted to do, you know, slightly harder and harder examples so that you're not just seeing the easiest examples in class. So here, you know, certainly trial and error is involved, but after a little bit of trial and error, we might guess to let u equal e to the x. The idea being, if I can replace this e to the x right here, I know how to integrate cosine of u. Now there's another e to the x, so let's see what happens. if u is e to the x, then du is e to the x dx. And so what I notice is I can take this e to the x right here, combine it with the dx, and that's my e to the x dx. That'll be my du. So, this is a little tricky in that we're not replacing every e to the x that we see with the letter u. In fact, the only e to the x, that we're replacing with the letter u is this one in here. The cosine of e to the x, that'll become a cosine of u. The e to the x dx, that'll become the du, and then hopefully we'll be able to integrate that. So also notice this is a definite integral, so I have to also change the bounds of integration. And once again, I can use the substitution here to find the bounds in terms of the u variable. So if x is equal to ln of pi over 6, I can take this value and plug it in here for x and solve that. If x is pi over 6, then u has, if x is ln of pi over 6, then u has to be pi over 6. And similarly, if x is ln of pi over 2, then u would have to be pi over 2. So here now we're essentially ready to completely convert the integral from the x variable to the u variable. So here as a preliminary step, I've factored out the 2 because I really don't need it. And the e to the x that's right here, that's outside of the cosine, I put it next to the dx because I'm going to make this e to the x dx now is going to become my du. The e to the x that's in here, cosine of e to the x, that's going to become cosine of u. And of course, these bounds, ln of pi over 2 and ln of pi over 6, we're going to convert to the u variable. So when we do that conversion, this is what the integral looks like. And so as I said, that ex dx is replaced with du, cosine ex becomes cosine u, and the bounds are converted to the u variable. And now, we reset. We look at this new integral and ask ourselves, okay, how do we do this problem? Do we just know the answer? Do I know the antiderivative of cosine? Yes, we do. So here we can just find the antiderivative, which is sine of u, and then I can do the f of b minus f of a thing. And hopefully I've got my unit circle, memorized, and I got my numbers correct there. Yeah, I think those are right. So yeah, so here, this was tricky because we're using the substitution u equal to e to the x, but we're not replacing every e to the x with u. Just this one that's inside the cosine. The other e to the x, so when we let u equal e to the x, then du is e to the x dx. So the other e to the x and dx, we combine, we put those together to become the du. So here, that little part is a little tricky where we're not just automatically converting every e to the x into the variable u. So this next one is similar. So here, certainly after some trial and error, we would guess to let the denominator be equal to 1 plus e to the x. It's not necessarily obvious, and at the end of the day, it works. And so, whether we could think of it or not, now that we've seen this example, we have to remember it, And the reason it works is because of how the derivative turns out. So if u is equal to e to the 1 plus, if u is equal to 1 plus e to the x, then du will be, the derivative of 1 is 0, the derivative of e to the x is e to the x, so du will be e to the x dx. And if you look by quote unquote coincidence, I have exactly an e to the x in the numerator that I can combine with the d to the x dx that's right there and make that e to the x times dx into a du. And the remaining term that's in the denominator, this 1 plus e to the x, that'll just become u. And then we've successfully converted the integral, then we'll see, okay, now can we find the antiderivative? But so here we go, starting with the original integral, I just moved the e to the x over, and certainly you don't have to do that. I just like to move it over just so I can now see very clearly that this part, e to the x dx, will be my du. And what's left, this entire denominator, well, that's what we're calling u, right? We said let u equal 1 plus e to the x. So this converts to 1 over u du. And now we know the antiderivative of 1 over u. Be careful, the antiderivative is natural log of absolute value of u plus c. So the absolute value is important when you're doing an antiderivative here. And then replace the u with its value as a function of x, right? We said u is equal to 1 plus e to the x. So I'm plugging that in for u. And then finally, I noticed that 1 plus e to the x is actually always positive. E to the x is a positive function, so I can just replace the absolute value bars with parentheses. If I left it at absolute value bars, that would be fine. It's not incorrect to leave the absolute value bars. So here, again, in this problem, we didn't just convert every e to the x into a u. I had this idea of reserving terms so that we've got, for example, the du taken care of. So here, the e to the x and the dx, I decided, okay, we're going to put those together because I know if I do that, that'll allow me to nicely convert these terms into du. So it's kind of just this one little extra kind of subtlety. It's not difficult, but if you haven't seen it before, then it could cause a little bit of confusion. So this is the last example here for this section on the exponential function. This is, a tricky problem. And as before, we're going to call the denominator, we're going to let that equal u. The idea being, 1 plus e to the x is kind of the most complicated part. So maybe we can make it simpler if we just replace it with a single variable. So now if I take the derivative, look what happens. I get du is equal to e to the x dx. But now when we actually look at the integrand, there is no e to the x. There's an e to the 2x. Okay, so here's, the quote unquote trick. So here, if we notice actually though, that e to the 2x, you can think of it as e to the x, the whole thing squared, which is the same as e to the x times e to the x. So that means I will have 1 e to the x that I can combine with the dx, and that'll become our du. If we combine one of these, 1 e to the x with the dx, that'll give me my du. But then we still have one more e to the x left over. So there's still this e to the x that's unaccounted for. The denominator is no problem. That'll be completely replaced with u. This entire term will be completely replaced with u, no problem. But this other e to the x, that's the only one that's unaccounted for. So we use a trick we've used before. Using the substitution, u equal to 1 plus e to the x, I can solve for e to the x. If I move the 1 over, I get e to the x equals u minus 1. And now I can replace this surplus e to the x that we had from the e to the 2x that didn't go with the dx to become a du. I can replace that extra e to the x with u minus 1. Then I will have successfully converted everything from the x variable to the u variable, and then we still have to try and see if we can do the integral. This is just converting the integral. We still don't know if this will actually be helpful, but of course it will, because I don't want to waste your time. So here's the original problem. So the first step I'm going to do is factor this, okay? So I'm going to rewrite that as e to the x times e to the x. So that's what I have down here. And then what I'm going to do is I'm going to put one of these e to the x's next to the dx and go ahead and just reserve it so that I know for sure I'm going to have my du. So now I know this will be my du, and 1 plus e to the x, that'll be u. That'll just be u. And finally, the term in the numerator I'll use the substitution and replace that with u minus 1. So when I convert the integral, that's what it looks like. The u minus 1 on top divided by u du. And so one comment I would always make is you should be sensitive to, when you have a fraction, you should be sensitive to when the denominator is a single term, especially in an integral. That's just something to watch out for. And if you see the denominator is a single term, something to always try is to break up the fraction. So here I write this as u over u minus 1 over u. U over u is just 1. And now we can take the antiderivative of each of these terms. The antiderivative of 1 du is u, and the minus, and then the antiderivative of 1 over u is ln of absolute value of u. Final step here, I'm going to replace the u with 1 plus e to the x, because I want my original answer to be in terms of the original variable of the problem, which is x. So I get 1 plus e to the x minus ln, and here I replace the absolute value with parentheses since I know 1 plus e to the x is positive. So minus ln parentheses 1 plus e to the x plus c. So that finishes that problem. And like I said, there's this sneakiness here where you have to factor the e to the 2x. And then there's a second level of sneakiness where one of the e to the x's is reserved along with the dx, so that that'll become the du. And the other e to the x, that's converted. That's written in terms of u. And so you can see these sort of the two different, roles. One of the e to the x's becomes a u minus 1, and the other e to the x combined, of course, with the dx becomes a du. And that's kind of a little bit of trickery here. But now that you've seen it, we have to remember it and, just be sensitive to it. So that ends the discussion on the natural exponential function. And so what we want to now do is generalize the idea. When we talk about the exponential function, we talk about e to the x, where e is the number, 2.7 ... Well, why do I have to use 2.7? Can I create an exponential function with a different base? So certainly, yes, we can, and it's called the general exponential function. So as I said, before we used e, which is like 2.718 ... to define this exponential function, e to the x, can't I now in general for any number a, so we will actually specifically use positive numbers, and I'll explain why in a second. Can't we define a function a to the x? And the answer is yes, otherwise why would I be talking about this? And so what we can do, and so this expression here in the box is basically the definition of a to the x. What we can do is we can define, using properties, a to the x is the same as e to the natural log of a to the x, because e and the natural log, you remember, are inverses. Here, these would cancel, and we would just get back a to the x. So I can write a to the x equals e raised to the ln of a to the x. That's no problem. That's just a simple identity. And then I can use the properties of the log and bring the x down. So this x that was up here, I bring it down in front. And so now if you look at this expression, e to the x ln of a, this is made up, everything here on the right-hand side, we know how to define. So for example, the natural log of a, we know how to define that. That's defined as an integral. That's the integral from 1 to a of 1 over t dt. So the other part is this exponential function, e raised to a number, this whole thing. E raised to a number, we know how to define that also. We defined that in the previous lecture. We defined the exponential function using the natural log function. So here, using things we've already defined, the natural log, the natural exponential function, and the properties of the log, we can now define, this general exponential function where it's a to the x, where a can be any positive number. And as I said, I'll mention why a is a positive number. So one thing I do want to mention is that this is just a notational trick. Think about the graph of e to the x ln of a, think back to chapter 1. When you multiply the x coordinate by a constant, remember ln of a is a constant, ln of a is a constant. When you multiply the x variable by a constant, that will cause compression or stretching in the horizontal direction. So here, a to the x is just e to the x, but rescaled, slightly compressed or stretched. So here it's really important to understand it's not really a new function as much as it is just a slight rescaling of an old function. And why would we want to do that? Because sometimes e to the x might not have the right shape for what we're trying to model. We might need to tweak that exponential shape to fit our data. And so now we have total flexibility, because here, as I said, we can define a to the x, and we can basically rescale it by ln of a, the original exponential function. So now we have a new function, a to the x. So Calc 1 starts all over again. What's the domain? What's the range? What are all the properties? So from looking at the scaled graph of e to the x ln of a, we can sketch the graph of a to the x. And if a is greater than 1, we can show you get an increasing graph. So here we have 10 to the x, 4 raised to the x, 2 raised to the x, 1.5 raised to the x. Here, a is greater than 1, and so we have these increasing exponential functions. Of course, every one of them, their shape looks very much like e to the x, just slightly stretched or compressed, slightly tweaked. If a is less than 1, then we have an exponential function that's decreasing. So here you see you have 1/2 raised to the x, 1/4 raised to the x. This is a decreasing exponential function. Finally, if a is exactly equal to 1, then we don't have a very interesting function. 1 to the x always equals 1. So here we just end up with the constant 1. So if a is equal to 1, then 1 to the x is just the constant horizontal line 1. So note that when a is equal to 1, it's not 1 to 1. Right? So I say here, it's continuous and 1 to 1, but not when a is equal to 1, right? So here, this horizontal line is definitely not 1 to 1. It fails the horizontal line test horribly. So why does a have to be greater than 0? Well, let me give you an example of what could go wrong if a is not greater than 0. Okay, so here I say, suppose a is -2, and let's look at this exponential function, -2 raised to the x. So far, so good. And so now here, let's cause trouble. So now I pick x to be 1/2, the input to be 1/2, and I want to look at f of 1/2, which now looks like -2 raised to the 1/2, or I end up trying to take the square root of a negative number, which gives us, a complex number. And since this is not a complex analysis class, this is exactly why we don't want to look at functions of the form a to the x, where we allow a to be less than 0, because we will end up having to deal with complex numbers, and we don't want to do that. So that's one restriction, why we want a to be greater than 0. The other comment I want to make is we generally don't really worry about the case where a equals 1. Because as I said, when you let a equal to 1, the function a to the x becomes 1 to the x. But for any real number x, 1 to the x is just 1. So in this case, our function is this boring constant. It's just a horizontal line. So, when we're looking at the function a to the x, we typically only look at positive numbers because we don't want to deal with any complex numbers. And we always typically look at where a is not equal to 1, because the case when a is equal to 1 is not interesting. It's just a horizontal line, One final comment I do want to make, and this is kind of a random comment right now. It's really for when we're in section 5.8. But I do want to mention that if we try to take the limit as x goes to infinity of 1 over x, in here, for each x, 1 over x equals 1. And so when I try to take the limit, we get the limit of 1 over x as x goes to infinity is 1. So another way to say that, and this isn't really math, I write here 1 to the infinity. That's really not a well-defined term because infinity isn't a number. It's okay to write it in a limit, but we don't want to write it by itself like that. 1 to the infinity equals 1. In a limit, you know, the limit of 1 over x as x goes to infinity equals 1. The only reason I bring this up is because later on the book will sometimes make it seem like that's not the case. And so I will mention this later. Okay, so you can ignore this now if you want. It'll come up, as I said, in 5.8. So let's find the derivative since this is a calculus class. And so one piece of analysis, you know, I hope that when you see y equal to a to the x and you think about finding the derivative, you say, aha, the variable is in the exponential position. And when the variable's up there in the superscript, in the exponent position, we need to use logarithmic differentiation. Because if I bring a natural log into this, then I can use properties of the log and bring the variable down from the exponent function. So starting from y equal to a to the x, we take the natural log of both sides, using the properties of the log, bring the x down in front. And so now we're in business. We can take the derivative of both sides. So one thing now I'll warn you is when you're taking the derivative of the natural log of y, remember y is a function of x. So natural log of y is actually a composition of functions of x, ln of f of x. So for the derivative, I need a chain rule. And remember, the derivative of ln of blah is 1 over blah. So here, the derivative of the outside will be 1 over y times the derivative of y, which is y prime. So we will get 1 over y times y prime. And so here's my derivative of ln of y. And now on the other side, be very careful. Remember that the natural log of a is a constant. A is a fixed number like 2 or 3 or pi. And ln of a will be a fixed number. Ln of 2, ln of 3, ln of pi, that's just a constant. So the ln of a, I can pull out completely. And I just have to take the derivative of x. And the derivative of x is just 1. So on the right-hand side, derivative x times ln of a is just ln of a. My final step here is I'm going to move the y over because I'm trying to solve for y prime. So I move the y over and then finally replace y with its definition. Y equals a to the x. So let me replace this y right here with a to the x. And so finally we get our derivative. So here, let me put it all together. The derivative of a to the x with respect to x is a to the x ln of a. And then here's the chain rule version. Suppose I didn't have a to the x. Suppose I had a raised to the cosine of x. So then I would do the derivative of the outside, which is a raised to the blah. The derivative of a raised to something is a raised to something times ln of a. That's just this formula right here. And then I want to multiply by the inside function. The inside function is u of x. So I multiply by the derivative of the inside is right here, u prime. So one thing I will mention, and in fact, this is pretty much kind of like my go-to move. Rather than worrying about this derivative formula, what I like to do is just take a to the x and go back to the original definition in terms of e. In terms of e, this is e times x, e raised to the x times ln of a. Remember that ln of a is a constant. So here, this just looks like e raised to some function of x. And to take the derivative of this, I just use a chain rule. It would be, the derivative would be e to the x ln of a, that's the derivative of the outside, times the derivative of the inside would be the derivative of this exponent, which is times ln of a. And I'll show you that in an example, but that's really, rather than learn new formulas, I always just go back to the original exponential function. So here's a quick example. So I find the derivative of 1/2 to the x. So I did this a couple of different ways, but the most direct way, so this one, the most direct way is just to do by definition. So here, this looks exactly like a to the x. So I can just copy down a to the x times ln of a. which is what I did. And here I rewrote it just so that it will look similar to, I'm going to do it another way. And so I want you to just to show you that we get the same answer. So I just rewrote it. So here I wrote 1/2 to the x. So remember, 1/2 is the same as 2 to the minus 1. And now when we raise this entire thing 1/2 to the x, so we're taking 2 to the minus 1, raising that to the x. And here, in this case, we multiply the exponents. Okay, when you have x to the m raised to the n, that's x to the mn. So this will be 2 to the negative x. So that's where I got this term from. And 1/2 is 2 to the minus 1. Certainly, if you want to bring the minus 1 down in front, you can. I just chose not to. And the whole reason I'm rewriting it is for this next method. So let me show you this next method. Here, we're doing a chain rule. As I said, I write 1/2 to the x as 2 to the minus x, but now I can't use this formula anymore. The formula is for a raised to the x, not a raised to the minus x, not a raised to the 1 over x, but a raised to the single variable x. So here, this is 2 to the minus x. I should see this as a composition. It's 2 to the x composed with negative x. Negative x is the inside function. 2 raised to something is the outside function. So derivative of the outside, so I just copy down the 2 raised to whatever times ln of 2. And then for the derivative of the inside is minus x, and the derivative of minus x is minus 1. And so I put the minus in front, right here. And then to make it look like the answer on the previous slide, right above, to make it look like this answer, this is a minus 1 that's in front of the ln, so you can actually bring it up to this exponent position. So this minus sign now moves up here. And you can compare these two now that you have the same answer. I just wanted to show you a couple of different ways to do the problem and a couple of different ways to look at this notation. You can also think of it this way. 1/2 to the x or 2 to the minus x. Either way, if we're consistent with our rules, we get the same answer. The antiderivative. So here, let me first show you that if we pick some number a, where a is positive, so that a to the x is defined, and a is not equal to 1. Why is a not equal to 1? Because I want to look at the derivative of this function. A to the x over ln of a. If a is not equal to 1, then the denominator will be well defined. The denominator will not be 0. So let me take the derivative of this, and I'm going to show you that we get a to the x. So as before, remember ln of a is a constant, so we can pull it out. So the ln of a, I took it out of the derivative. That's a constant. Then we take the derivative of a to the x, which we know is a to the x times ln of a. And here we can cancel the ln of a's because they're constants. And so after canceling, we get that the derivative of a to the x over ln of a is just a to the x. So this gives us an antiderivative formula. If I now slap on an integral here and here, the integral and the derivative cancel, and I get my antiderivative formula. Antiderivative a to the x equals a to the x over ln of a plus c. And we can write the u subversion, if you like, a to the u, and a derivative a to the u du is a to the u over ln of a plus c. And again, I'm going to mention, and I'll show you, I'll do this in an example here. The way I like to do it is I would just rewrite a to the x as e to the raised to the x times the constant ln of a. And then do the integral that way. To me, since I already know how to work with the exponential function, rather than kind of reinvent the wheel, I just convert back to the exponential function. But of course, we should understand both ways. And at the end of the day, you should do what works best for you. So here, there's actually, I do this in two different ways, but the most straightforward way here would be just to write this as 1/5 raised to the x dx, and then just directly use this rule. because then it's in the correct form. And so you'd get, the answer would be 1/5 raised to the x times 1 over ln of 1/5. So that'd be the most direct way, but let me show you. So here, for 5 to the minus x, I said, oh, well, this is a minus x, it's not an x, so let me do a u substitution. Let u equal minus x, then du is minus dx. And so now I can, here, I'm missing the minus sign, so I multiply on the inside and on the outside by a minus sign. That's just how I like to do it. Some people like to solve for the dx, and I'll do that when I do method 2, just to show you a variation. And so here we can convert the negative dx into du, the 5 to the minus x into a 5 to the u, and of course copy down the minus sign that's in front of the integral. Now I can use our formula. So now this looks like something we have a formula for. So copy down the minus sign that's in the front, and the antiderivative 5 to the u is going to be 5 to the u over ln of 5 plus c. Very last step. The original problem is given to us in the variable x, not the variable u. So I can't give the answer in terms of the variable u. My very last step, I plug back in for u. And we should be able to take a derivative and get back the integrand. So for method 2, this is what I'm talking about. This is kind of what I prefer to do in general. Is this 5 raised to e to the x, we know I can write this as e to the ln of 5 to the minus x, because e and ln are inverses. They would cancel, and you just get back the 5 to the minus x, okay? And so the whole reason I do this is now use properties of the log and bring the x down. This minus x, I bring it down in front. And now I've converted the problem. So now it's a new problem. Now I'm trying to find the antiderivative of e to the minus x ln of 5 dx instead of this problem. I've converted it. And now I just do the same thing. I only know the antiderivative for e to a single term up here. So let me call that entire exponent, let u equal negative x ln of 5. Then du is negative ln of 5 dx. Remember, ln of 5 is just a constant. So it's okay if I don't have the ln of 5 in my integral, I can multiply it and divide it out. Or, in this case, let me do the other style of integration. Here, I'm going to solve for dx. Dx equals du over negative ln of 5. So here, let me replace. So I'm going to replace this negative x ln of 5 with u. And the dx, I'm going to solve for dx. If you solve for dx in this equation, you get dx is du over negative ln of 5. So that's what we have here. E to the u times negative du over ln of 5. The minus 1 over ln of 5 is just a constant. Pull that out. What's left now, we have something where I know the formula for the antiderivative e to the u. It's just e to the u plus c. So technically, the minus 1 over ln of 5 multiplies to the e to the u and to the c. But since negative 1 over ln of 5 is a constant times a constant is just another constant. So we just call it c again. And very last step, I replace the u with the original substitution, negative x ln of 5. And we get back the same answer. Remember that this and this are the same thing, just written in 2 different ways. In fact, e to the minus x ln of 5 is the definition of 5 to the negative x. So these are identical. And so, yeah, one option is to convert it to e, or the other option is to learn this new antiderivative formula. You got to be able to do it one way or the other, or the best, be able to do it both ways, right? So I like to know, both these tricks, where I can convert it or I can use the other formula. So let's talk about the inverse here. So for this function a to the x, because the graph, it's just e to the x, but it's been rescaled. And obviously, e to the x has an inverse. E to the x is 1 to 1. So here, a to the x will have an inverse, and we can find it just by reflecting it. If a to the x is just the exponential function rescaled, stretched, or compressed, and the inverse of e to the x is ln of x, then the inverse of a to the x is basically just going to be ln of x rescaled, stretched, or compressed. And and I'll show you that. We'll get a formula that'll show you that explicitly here in 1 second. So here, I just want to write down the behavior of the inverse. So, because now we have a new function. So this is the notation for the inverse of a to the x. The inverse of a to the x is denoted as log of x base a. And we can see the graph is the best thing to get all the basic information. So here you can see the domain is x has to be greater than 0. So we're looking at this curve here that's been reflected, that's crossing the x-axis. You can see the domain is x has to be greater than equal to 0. You can see that the range is all of R, you can see here, it'll be decreasing if a is greater than 0 and less than 1, and it'll be increasing if a is greater than 1. We have the same inverse relationships as the exponential function and the natural log. A raised to the log x base a. So here, the base a and the log cancel, and we get back x. So that's very similar to, e to the ln of x is equal to x. And the other way around too. Again, a to the x is just a rescaling of the exponential function. Its inverse then is just going to be a rescaling of the natural log function. So we expect these things to have inherited all of these properties from the natural log and the exponential function. So here, log of a to the x base a is just x. Again, the log base a and the exponent cancel. It just returns back the original input x. So here you can just write it in one statement like this. And you should be able to go back from one end to the other. From the left equation to the right equation, take the log base a of both sides. Then I get log base a of y equals log base a of a to the x, which is just x. And to go from the equation on the right to the left, raise both sides to the a. So here I have a raised to the log y base a, which is just y, equals a raised to the x. And this is that inverse relationship, where we can go back and forth. And so the natural log in this notation can be viewed as the log where the base is e. So log base e would now be the same as the natural log. And just a general comment, in science books, typically when you just see log x by itself, that's typically base 10, unless it's a computer science book. Computer science books, if you just see log x, it's usually base 2, because binary is base 2. So here's the change of base theorem that I mentioned, that we can relate any logarithm of any base to any other logarithm of a different base. So here, suppose we have numbers, positive numbers a and b, and assume they're not equal to 1, because if 1 to the x is not invertible because it's a horizontal line. Then for any x greater than equal to 0, here's the change of base theorem. Log of x base a equals log of x base b divided by log of a base b. So the number one thing I want you to notice is the only variable is right here is the letter x. And this thing in the denominator, log of a base b, a is a constant, b is a constant, log of a base b is just a constant. Okay, so here we've written log of x base a, we've just written it as log of x base b, but rescaled, divided by this constant. So the proof is not difficult. So here I say for any x greater than 0, we can write x as equal to a to the r. Okay, so how do I get that? So if you look at the a to the x function, if you look at its range is all positive numbers. So now if you pick any positive number, pick an x anywhere here, pick a positive x, I should be able to go back to the function and trace it all the way back to an input on the real line. I'm going to call that r. And so here, x would be a raised to the r. So this is the r down here. And it's because since x is positive and the range of a to the x is all positives, I can write x as a to something, for some input, call that input r. So now let's take the log of x base a. So I do log of x base a, replace the x with a to the r. We know log of a to the r base a is just r. So that's 1/2 of it. Now take the log of x base b. So here we have, I replace the x with a to the r, because x equals a to the r. And using properties of the log, I bring down the r. And now solve for r. So in both equations, solve for r. For this first equation, it's easy. Log of x base a equals r. For the second equation, I'm trying to solve for r. So I'm going to divide log x base b by log a base b. That'll give me r. So there's r from the first equation. And here's r from the second equation. If we set, and they're both equal to r though. So we can just equate the ends. If you equate the ends, you get log of x base a equals log of x base b divided by log of a base b. And in our book, they specifically choose b to be the Euler number e. And so if we make b here into the Euler number e, then we get log of x base a equals ln of x divided by ln of a. So in our textbook, we always just convert to the natural log because we know how to differentiate the natural log. And so, yeah, in our textbook, we're typically going to always write, if I have log of x base 12, I can write that as ln of x over ln of 12. And keep in mind, ln of 12 is a constant. If I have log of x base pi, I can write that as ln of x over ln of pi, and then take the derivative or what have you. So here, let's do some quick problems just to practice here. So here we have 6 raised to the x minus 3, and I'm trying to find the x minus 3. So what I like to do is isolate the term with the unknown, which is 6.1 to the x minus 3, and then move everything to the other side, so it's equal to 36. And now remember the unknown is up in the exponential position, and so we have to use logarithms. You can use the log of any base, but since we're using logs of different bases, not just e, here the easiest thing is to do log base 6.01. Then on the left hand side they cancel out completely, so I just get x minus 3. On the other side I brought the 2 down, but you don't have to. And then I isolate the x, and I found x. For the derivative, let me show you how we use the change of base theorem. For the derivative, I go from base 2 to base e. I write log of x squared base 2 to ln of x squared over ln of 2. Remember, ln of 2 is a constant. So I can just pull that out. So I pulled out ln of 2. And now I just need to do the derivative of ln of x squared. Remember, this is a composition of functions. So I need to do the derivative of the outside, which is, so the 1 over ln of 2 is this constant right here that I just copied, okay? So here I'm going to do derivative of the outside, which is 1 over x squared times the derivative of the inside. Derivative of x squared is 2x. Certainly you can bring the 2 out in front and then take a derivative, you'll get the same answer. So yeah, the derivative of the inside is 2x. So here I put everything together, and there's your derivative. And that's why change of base is useful. You change the base into the natural log, and that we know how to work with. So for example, here, this is an integral with log base pi. I don't know about log base pi, so I'm going to write log of x plus 2 base pi as, so I wrote this log of x plus 2 base pi as ln of x plus 2 divided by ln of pi, where ln of pi is a constant. And so now I'm going to let u equal ln of x plus 2. So this part here with the variable. Then du is 1 over x plus 2 dx, and we have the 1 over x plus 2 dx. So we're ready to completely do this integral. So first I convert it to base e and factor out the constant, 1 over ln of pi. The remaining terms will be converted. ln of x plus 2 will become u, and this part will become du. Integrate, I get u squared over 2. I copy the 1 over ln of pi, and then replace the u with what we originally substituted for. Remember, this square here is on the outside. All right, everybody. So I'm going to stop right here. I have one more slide, which I'll continue next time, but you can read ahead if you wish. And so I'm going to stop right here.